So as the name suggests, the course is on the theory of information. And I'll define precisely, as we go through the course, I'll precisely define what we mean by information and why it's important to measure information and how it's useful in a range of different problems. All right, so information theory has a long history. It was formally developed in 1948, so it's a very old theory. But it's seen applications in a number of different fields, very wide variety of fields. And the original motivation for information theory was for two problems. How do you compress data, and how do you transmit data from one place to another in a reliable fashion, even in the presence of noise? And this is fundamentally what we will cover in this particular course. We'll focus on these two problems in some depth, some level of depth. But we'll also see how this can be applied and how these ideas can be used in a range of different problems. So what is the data compression problem? The data compression problem is the following. Suppose I give you a class of files. Let's say these are text files, and you know that these text files are basically English text. You have some information about what kind of files you want to compress. So the compression problem is you're given some file, some text file. The goal is to produce some other file, a compressed version of this file, which has as small a file size as possible, but at the same time you should be able to recover the original file from this compressed file. All right? I'll make these things more precise as we go along, but that's what you've seen. If you use something like zip or gzip and so on, all of these are tools that do what I call lossless compression, in the sense that you can recover the original file exactly from this compressed version of the file. All right. So for this problem, there's also lossy compression, where the goal is not to recover the exact original file, but maybe some slightly perturbed version of the file. For example, in images, right? So let's say you take a picture using your phone, and let's say you upload it on WhatsApp. If you notice, the quality of the image that is shared on WhatsApp is usually lower than the quality of the original file. If the original file is, let's say, a few megabytes, then typically what you share on WhatsApp is, let's say, a few kilobytes or so. So internally, WhatsApp is doing some kind of lossy compression. The quality is reduced, but the file size is also significantly reduced. So given this, how small can you make it? Right? How do you design an algorithm for compression? We look into that as well. But primarily, we are also interested in how small can the compressed file size be. Suppose I want a certain level of quality, then is it possible to make the file size arbitrarily small, or is there some kind of a fundamental limit? That's one of the questions that we will address in this course. The second class of problems is in digital communication. So after all communication that happens, whether it's along wires or cellular communications or Wi-Fi, all of this happens over noisy media. Right? So noise is something that we can't control, but we have a rough estimate of what the level of noise is. So given that we have a certain level of noise in digital communication parlance, you're given a certain signal to noise ratio. What is the maximum rate? What is the maximum throughput? How many information bits can you transmit per second? All right, in such a way that you can recover the transmitted data reliably. So if you have, let's say, voice communication, you want to be able to recover what is being sent. Right? Or if you're trying to download a file over your 5G or Wi-Fi, you should be able to recover the file that you recover on your phone is exactly the same as what is there in the central server or what has been transmitted. All right? So all of this happens despite the presence of noise. And in practical communication systems, the signal to noise ratio is actually pretty low, because after all, communication has to happen over very large distances. Right? Despite this long distance communication which is very noisy, you still have very reliable communication, and that too at a very high rate. How is this possible? That's one question that we'll address. And not just that, we'll also try to quantify how much information is actually, how much information can you actually transmit per second. It turns out that you can't make it arbitrarily large. And that's reasonable to expect, right? If there is a certain level of noise which is random and you can't control, then it shouldn't be possible to raise your data rate arbitrarily high. And we'll try to quantify what is the maximum throughput that you can possibly achieve. So these are two primary questions that we will try to address in this course. But then there are a lot of other questions that can be answered using information theory. And here are some representative questions. So it's very widely used in cryptography. So let's say that I want to keep a secret, or I want to share a file secretly. What does it mean to be secret? Right? How do you define security? There are multiple definitions. There's an information theoretic definition of cryptography, and there's also a computational complexity definition of cryptography, and both of them are used based on what application you're looking for. All right. It's also used in investment or gambling. So let's say that in these scenarios, let's say you want to invest in, let's say, stocks, or you want to play roulette or some other kind of game, blackjack. Inherently, there's some sort of uncertainty or some randomness in the system, because you don't know. Let's say you invest in a particular stock, you don't know how much returns you're going to get over a period of time. So you can model this as some sort of a random quantity. All right. So if you have a reasonably good model, then how much payoff can you expect in a certain amount of time? Right? That's one question that you can ask. In machine learning, again, you're given some data and you want to learn from this data. In other words, you want to design a good predictor, which, given some new data, which is not coming from your from the data set that you have access to, what is the best level of prediction that you can possibly obtain? Right? In algorithms, let's say that you want to know what is the best possible runtime you can get for executing a particular task in the presence of some kind of uncertainty. In physics, it's used in quantum mechanics to find out to quantify how much uncertainty there is or how much disorder there is in a particular system, and how do you control this. It's also used in neuroscience. So for example, the eye is taking in information from the outside world, and all of this is being communicated through neurons to your brain. So if you wanted to quantify how much information is being transmitted from the eye to the brain, of course, you need a definition of information or a measure of information for that in the first place. But this is also a question in computational neuroscience that also sees applications of information theory. All right, so this is just a small sample of applications of information theory, and we'll see more as we go through the course. All right. Any questions so far? Okay. So I gave you a number of applications, but one common thread through all of these is, as we'll see, is the following. There is some kind of a system where there is some randomness that is inherent to the system. All right. In data compression, you're given a file. There's some uncertainty as to what the file is. If you know beforehand that there's only one file that needs to be compressed, then we'll see it becomes a trivial problem. But there's some class of files, and we'll model this in some kind of a probabilistic fashion. In digital communication, the randomness comes from the noise that is present in the system. So there's some randomness there as well. In cryptography, again, there are typically two sources of randomness. One in the source, that is what file you want to compress, that can be modeled as a random source. And also in the algorithm, you are allowed to introduce some extra randomness when encrypting your file, for example. In investment or gambling, again, there is some uncertainty in what kind of payoffs you can get. In machine learning, once again, the randomness can either come from the algorithm, depending on what kind of a problem you're looking at, but also fundamentally in the source. The same holds true for in algorithms, in physics and neuroscience. So in all of these, there is some randomness present in the system that you can't control. But in all of these, we'll assume that we can model the randomness. That is, we know the statistics or the distribution of the source of randomness. And in all of these, what we want to do is design some kind of an optimal algorithm. There's some measure of what is good. In data compression, the measure is the compressed file size. You want that to be as small as possible. In digital communication, you want to transmit at a rate that is as large as possible. In cryptography, you want to keep the file as secure as possible. In investment, you want to maximize your returns. In machine learning, again, you want to minimize your prediction error. In algorithms, maybe you want to minimize the runtime. In physics, you want to minimize the amount of disorder. And in neuroscience, you want to make sure that as much information is being sent to the brain or whatever system you want to design as possible. All right? So two common points in these are, one, there's some inherent source of randomness, which you have a model for. And the second is there is some notion of optimality for an algorithm that you want to design. So given this, the first question we want to address is, what is the best that we can possibly do? All right. And the second question is, how do we design an algorithm that achieves this best possible limit? So to motivate this a little further, let's take the example of data compression. So one way of approaching the problem of compression is the following. I'm given some class of files. I'll come up with an algorithm, some algorithm. And then I'll try to improve. So that gives me a certain compression level for a class of files. Then I try to come up with a new algorithm, which hopefully does better than the old one, and so on and so forth. But at what point should I stop? How do I know if I've hit the limit or not? Right? That's the question that we'll try to first address in information theory. What is the best that you can possibly do? That is, no algorithm can possibly do anything better than this particular level of compression. All right? For that, we'll need some kind of a model for the system, and we'll do that eventually. And we'll do that for communication as well. So given a particular model for noise, what is the maximum possible throughput that we can achieve for this system? So the main benefit of doing so is that now if somebody comes up with an algorithm, then you know how close it is to optimality. And also if somebody claims that they're going to do better than this, then it means that either they're lying to you or they're working fundamentally on different assumptions than you are. All right? Okay, so first, with that out of the way, let's first try to get some intuitive sense of what we mean by information, or how do we measure information. So as I said, in all the systems that we'll consider, there is some amount of randomness. And I claim that the more randomness there is in the system, the more information you can possibly get out of it. All right? To understand that a little better, let's consider the following example. So let's consider this problem where you want to guess the next letter in this sequence of letters, in this word. So in the first example, the first letter is Q. What would be your guess for the second letter? U, right? All of you more or less said U. Right? So now if I say that the second letter is U, you didn't get much information out of it because you knew it was very easy to predict what the next letter was. Let's take the other example. A followed by something. What would be your guess? P? Why P? Why not R? Why not S? Why not B? So, okay, what's your guess? Okay, suppose you guessed P and I say it is B. Then now you got more information about what the word is. So initially, you didn't know what this word was, right? But when I said that the second letter is B, you got a lot more information about what the rest of the word is compared to what you had before. In the first example, when I say that the second letter is Q, you didn't really get much information because it was a very easy guess, right? And the reason was, prior to me telling you what the second letter is, you had a lot more uncertainty in the second example than in the first example. In the first example, there was almost no uncertainty as to what the second letter should be. Right? So we'll define information in this particular fashion. You get more information if it reduces the randomness or uncertainty about the system more. All right? I'll make this more precise as we go along. And one of the ways we'll define this is through this problem of data compression. Okay? So again, as I said before, the data compression problem is the following. You're given some raw file. For now, we'll assume that these are text files. Let's also assume that these are English text files for now. And let's say I use a particular tool to compress the file, maybe zip. All right, so I'll zip the file. I take the compressed file size and divide it by the raw file size and see what this ratio is. I call this the compression ratio. The goal is to design an algorithm that gives as small a compression ratio as possible. That's going to be our primary goal. Okay? It's helpful to think of this in terms of a block diagram. So we're given some particular source. Let's say it consists of n symbols. These could be n bytes or n bits or n characters. And all of this is captured by some particular, you know what the source alphabet is. That is, if there are n characters, then this script X is the set of all possible characters from which the text can be drawn from. Or if I treat this as a sequence of bytes, then the script X is the set of all possible values a byte can take. Okay. So we're given a file of size n. I say that it contains n symbols. The goal is to design two algorithms, a compressor and a decompressor, or an encoder and a decoder, which does the following. So the compressor takes this raw file as input and outputs a compressed file, which is a sequence of k bits. Okay? And the decompressor or the decoder takes this compressed file as input and outputs some file, which I call xn hat. This xn hat could potentially be different from the source file. When I say lossless compression, this xn hat should be exactly equal to xn. In lossy compression, I allow it to be a little bit different from xn. Okay, so that's the fundamental premise. And the compression ratio can also be measured in terms of the rate, which I'll define to be k by n. So the n symbol file is compressed to give a k bit file. So I say that the rate is k by n bits per symbol. Okay. We'll explore all of this in a little more detail, but I'm gradually introducing you to the notation and some of the concepts that we'll see in the rest of the course. All right, so that's the data compression problem. And you've all used data compression tools before. All right. So I'll give you an exercise which you can do at home, which is take any English text file, all right? It should be English text, and the file should have size at least a kilobyte or so. Something that's reasonably large is better. The larger the file size is, the better. And it should be valid English text. For example, you can take a novel like War and Peace or any other novel in .txt format, compress this, all right? Take a bunch of different files, maybe different novels, or maybe articles from Wikipedia or something else. Compress each of these files and compute the compression ratio, that is the ratio of the compressed file size to the raw file size, all right? And maybe by next class tell me what you get. My claim is that no matter which English text file you take, if the file size is large enough, then this compression ratio is going to be roughly the same. So whether you try to compress War and Peace or you try to compress Harry Potter, you will end up with the same compression ratio. All right. In fact, you take any sufficiently large block of English text, the compression ratio is going to be roughly the same. All right, at least to the first order. And we'll see why that is the case later on. So for now, let's run the following experiment. I'll generate a sequence of Bernoulli symbols. So I'll try to generate a text file or some text which consists of two symbols, maybe just 0 and 1, and compress it using a standard file compression utility. And we'll see what the compression ratio is for different values of the Bernoulli parameter P. Okay? And my claim is that if there is more uncertainty in the source, that is the source looks more random, then it is harder to compress. The less random the source is, the easier it is to compress. Okay, that's my hypothesis, and we'll try to verify that hypothesis now. But before I even do that, for what value of P do you think the source is most random? Half, right? Because it's a coin toss. You don't know, with equal probability the next bit could be 0 or the next bit could be 1. Which one has the least amount of uncertainty? 0 or 1, right? So that's because you know exactly what the rest of the sequence is. It's going to be all zeros or it's going to be all ones, right? So if I had to plot the compression ratio versus P can take any value between 0 and 1 and half. As you the hypothesis is that this curve, the optimal rate versus P curve, it's going to peak at P equal to half, and it's going to decrease on both sides. All right. How do you think it's going to increase or decrease? Linearly, quadratically? Any guess? Sorry? Okay, let's see what happens. All right. But hopefully you all agree with me that intuitively the rate should increase, or the compression ratio should increase as I go from 0 to half, and should decrease as I go from half to 1. Which? We'll see. Maybe it's a parabola, or maybe it looks. That's assuming that it behaves as the variance. It's Bernoulli, I agree. We see that it's not exactly a parabola. It's something else. All right? Let me see this. So I'll vary P from 0 to 1. I'll skip exactly equal to 0 and exactly equal to 1. And I'll try to do the following. Let me also declare something for equal to P. So first I'll try to generate a random Bernoulli sequence of a particular length. So let me take n equal to something small for now. I'll start with say n equal to 32. And let's say that my raw sequence is so I'll choose the symbols to be either 0 or 1, character 0 or character 1, the size being equal to n, and the probabilities being character 0 is taken with probability p, and character 1 is drawn with probability 1 minus p. All right. Now this is just a sequence of characters, and I'm using some kind of a file compression utility. So I need to convert it to a format that can be taken as input to this file compression utility. All right. And so the ith compression ratio, I'll simply take this to be the length of the compressed file and divided by the length of the raw file. All right. And I'll just plot P versus the compression ratio. I'm just using some standard text compression utility. This is called Z standard, but you can replace this with zip or LZMA or any other utility that there is. You won't see too much of a difference. All right. And so let me do something else. So I have this compression ratio. I'll normalize this compression ratio. so that the maximum compression ratio that I get is 1. Okay. The main reason why I'm going to get a different compression ratio is because of the way we are converting these sequences to bytes, and then the way the file, this particular algorithm Z standard is treating this kind of objects that are being converted. But let's just run this file. Okay. This is so basically it seems to be all over the place, right? Hopefully you can see it at the back. Great. So there's not much of a structure, but then I've also chosen a very small file size, and I'm drawing the files at random, so there is some amount of variance that you can kind of expect, right? But let me do the following. Let me just increase the file size, nothing else. I'm just increasing from n equal to 32 to 1024. Now I get something that's much more smoother. All right. Even if I, now let's say I increase this even further, let's say 2 to the power 14. Now I get something that looks like a very smooth curve, which almost looks like a parabola, but as we'll see is not quite one. And this holds true. So every time I'm running the code, I'm generating a new random sequence, right? But it doesn't matter. As long as the file size is large enough, even though it's a different file that I'm compressing every time for a given P, I still get the same compression ratio. All right, let me do something more. I have this 0 and 1. Let me change it to something else. Instead of 0 and 1, let's say I have A and B. Okay. Doesn't matter. I still get the same. Right? I'll plot something else, a function that we'll see later on. Which is minus P times log P minus 1 minus P times log of 1 minus P. Okay. We see that it's an almost perfect fit, and if I increase the file size even further, it's going to match exactly. Right. So it appears that I use this file compression utility to compress Bernoulli random sequences. I seem to get the compression ratio that behaves as this weird function, which is minus P log P minus 1 minus P log 1 minus P. Right? This particular function has a name. It's called the binary entropy. And we'll see that the entropy is going to be a very fundamental important quantity that we'll see in the rest of this course. Okay. So just for reference, the binary entropy, which we'll denote as H2 of P, is minus P log P to base 2 minus 1 minus P log to base 2 of 1 minus P.
Can you explain the code again?
So let's maybe quickly walk through the code once again. So basically in the initial part, so for each value of p, I'm basically generating a random sequence of length n, where it's a Bernoulli sequence, but the symbols can be anything you want. It can be a comma b or 0 comma 1 or c comma d, anything. All right. So I'm generating an n length random sequence which are drawn with probability. So a is drawn with probability p, and b is drawn with probability 1 minus p. The next line basically just converts this sequence into a stream of bytes. It's formally called a byte object, and it's doing nothing else but just transforming an array to a sequence of bytes. And this is fed to this compression algorithm. The compression algorithm takes a sequence of bytes as input, compresses it, and gives a sequence of bytes as output. And basically what I'm doing here is taking the ratio of the compressed file size to the original file size. All right? And just plotting this, nothing more. All right? Any other questions?
The rate depends on the compressor.
The rate, in fact, it won't. Even if I replace Z standard by zip, you will get roughly the same thing. I mean, there'll be minor variations, but they're negligible if n is large enough.
I mean, it doesn't depend on the algorithm.
As long as it's a good algorithm. So if it's zip or it's gzip or Z standard or LZMA, all of these are good compressors, and all of them are going to give you roughly the same performance on these kind of files. There are further optimizations done in each specific algorithm, but we are not worrying about that for the moment.
So any good compressor will give you a rate like Pn.
Yes. If you choose a bad compressor, I agree. Like you can come up with some random compressor and that is not going to give you the same level of performance. All right. And we'll see why I call these good compressors. They're good in a certain sense, under certain assumptions. Any other questions? Which one? If it's compressed, then it should be less than 1. That's because of the way it treats certain byte objects. The way it's the kind of object that is being fed as input. Okay, so this is potentially less, it's going to be less than 1, but it could potentially be even smaller than 1. Right? For example, this could be 0.9, but I'm normalizing it so that the maximum value is equal to 1. That's the only thing. All right?
What is the maximum value of the compression?
I can just find out. So let me just. So it turns out to be something that's significantly less than 0.2.
Does this depend on the compressor?
This could depend a little bit on the compressor for other reasons, depending on implementations. But if you increase n, it will not really depend on the compressor. This is more of an artifact of what the alphabet is, because it's treating this as a sequence of ASCII characters whose alphabet is much larger, whereas what we have is just a Bernoulli source which has only effectively only two characters. That's really the main reason why you're seeing a difference. If you were designing a compressor specifically for Bernoulli sources, then the compression ratio would be 1 effectively. Because here, every 0 and every 1 is being converted to ASCII 0 and ASCII 1. So you're not using one bit to represent 0 or 1 in the raw file. You're in fact using a whole byte to represent a 0 and a whole byte to represent a 1. So these are all minor stuff. That's why it did the normalization. All right. Okay. So the second canonical problem that we'll be looking at is communication. So if you take, let's say, traditional voice communication, telephonic communication as it was developed, a reasonable model for the system, the channel, is the following: y of t is equal to a times x of t plus z of t. So at a given time, you're transmitting some kind of a signal x of t. What you receive is scaled or attenuated, and there's some amount of noise that is being added to it. So the noise being added, there are various sources of noise that can typically get added in the communication system, but one of the primary sources of noise is receiver noise. So in your receiver, there's an amplifier, there's a whole range of circuitry, and that contributes to the most additive noise in the system. All right? And all of these can be estimated. So you can estimate what is the level of noise. You can't estimate the noise signal, but you can estimate the noise power. So that is known, and it depends on the receiver that you're using. This A is an attenuation factor that typically depends on the distance. So the farther you're away from the source, the less receive power you get, and therefore the smaller A is going to be. All right. Typically this decays as 1 over distance square. Okay. So in such a scenario, I mean, think back to the 1950s, where you didn't have a lot of sophisticated hardware, and you wanted to design a system where you could communicate reliably in presence of such a noisy medium. All right. So then the problem is, let's say I want to transmit over several kilometers, then what do I do? Because the noise level remains roughly the same irrespective of how far I am, but the attenuation factor only increases. And typically you could be in a scenario where the ratio of the power of this part of the signal to this part of the signal could be significantly lower than 1. The farther you're away from the transmitting source, the worse it's going to get. All right? So then what do you do? What is a potential solution that you can think of? Yeah? Yeah, so that's one of the common approaches that was used. Basically, you use what is called a repeater, wherein now I want to transmit over 10 kilometers. Maybe what I can do is, after every single kilometer, I place a repeater which is going to receive, amplify the signal, and then transmit again, retransmit. So now at least the signal power gets boosted. But the problem is, you're not just boosting the signal power, you're also boosting the noise power. Right? So it only gets worse. The more repeaters you put in, the signal power is now great, but your noise power has also increased significantly. And that's proportional to the number of repeaters that you put in between. All right? So then what do you do?
Diversity.
Sorry?
Diversity, like we can,
But what is diversity?
we can use the different transmitters to different directions. Same transmitter, but in
Again, it doesn't matter, right? All of this is just dependent on distance. Assuming you have perfect line of sight communication.
you can average out all the
In fact, you can't. It's a nuanced topic, but you can get diversity only if there is sufficient change in the statistics, typically different channel coefficients, right? Which you can't get in line of sight communication. All right? So how do you do reliable communication? The point is you can do reliable communication by going, instead of viewing this as an analog signal, you employ digital communication, right? And what do I mean by that? Let's suppose that all of the communication, these symbols x of t, are bits. So instead of just simply amplifying or boosting the received signal, I can try to recover the sequence of bits, right? So then hopefully I get a clean sequence of bits, and which can now be boosted and retransmitted, and hopefully that is going to help. All right, but we'll see later that even that is not sufficient. It doesn't ensure that you can get reliable communication. It requires something additional, which is adding a certain amount of redundancy to the information, or what is called an error correcting code, in order to get reliable communication. All right. So these are the two canonical problems that we'll look at in this course, but in doing so, we'll also look at a host of other problems. For example, how do you distinguish between two different signals in the presence of noise? And we'll see that that's a fundamental component that appears both when you're talking about compression as well as communication. All right? Any questions so far? Okay. So now we'll take a little bit of a detour. We'll just see some of the prerequisites that we need, and then we'll go back to these problems of compression and communication. So hopefully in probability you've seen all of these topics. I assume that you know all of these concepts. What is a random variable? What is a discrete random variable? What is a continuous random variable? What is a probability mass function? What is a probability density function? What is a cumulative distribution function? How do you transform different random variables? So if I give you a random variable with a certain PDF, then can you find the PDF of, let's say, x square or square root of x or something else? And you should know, let's say, Bayes' theorem, conditioning, what is expectation, mean, variance, and moment generating function. What do I mean by independence of two random variables or independence of two events? And some common distributions, like what is a Bernoulli distribution, what is Gaussian, Laplace, chi-squared, and so on. All right. So these are some basics that I will expect, and we'll try to cover some of the other stuff very briefly. So one often neglected tool in probability is the union bound, which basically says that if I have two events, A1 and A2, then the probability of A1 union A2 is less than or equal to the probability of A1 plus the probability of A2. All right. It's a very simple bound, but as you'll see, it's very powerful, and we'll be using it again and again. If you've done any amount of digital communication or wireless communication, you'll see that it's very widely used, for instance, in upper bounding the probability of error. Right? You can express probabilities of error as sums of pairwise error probabilities, and that's something that we will use in this course. All right. So we need a certain amount of rigor in probability that is sometimes covered in a basic probability course, sometimes not covered so much. And this will be very important when we talk about continuous random variables and defining information measures for continuous random variables. Discrete random variables are very nice, easy to work with, but as soon as we go to the continuous domain, you'll see that we need to be a little more careful in doing many things. So hopefully in your probability course, you've seen what a probability space is. Is there anybody who has not seen these omega fp? Okay, that's good. So what is omega? Okay, it's the sample space. And what is the sample space? So it's a set of all possible outcomes of the experiment. So in the context of tossing a coin, it's going to be either head or tail. For rolling a die, it's going to be a number between 1 and 6. Let's say I use a random number generator to generate numbers between 0 and 1. Then the sample space could be the interval from 0 to 1. All right. What is F? It's called the event space, and it is expected to be a sigma algebra. So what is a sigma algebra? Can we be a little more precise? So what is F? What kind of an object is F? So firstly, F is a collection of subsets of omega, right? And this collection of subsets is supposed to be a sigma algebra, or it has to satisfy the following properties. What properties should F satisfy? Yeah, I hear multiple things. Yeah, one person. Okay, so if any A is an element of F, or A is an event in F, then the complement should also be an event. Right? The objects in F are called events.
Should be closed under finite unions.
Closed under finite unions. Countable unions. I'm sorry?
Phi and omega should be present.
Correct. So omega should belong to F. By property 2, if omega is in F, then the empty set, the null set, should also be in F. The third property is that if A1, A2, and so on, if I have a countable sequence of elements or events in F, then their union, it's a countable union only, should also be in F. All right. So why do we need to formally define the event space? Okay, so let me pose this a little differently. So let me denote 2 to the power omega to be the power set of omega. That is the collection of set of all subsets of omega. So my question is, can I always just take F to be 2 to the omega, the power set? Okay, so how many say that I can always take F to be 2 to the omega? Nobody? How many say that I cannot take F to always be 2 to the omega? What about the rest? Okay, why can't I always take, so firstly, in what scenarios can I not take F to be 2 to the omega? Okay? And why? I guess some of you have already taken the concentration inequalities course. I don't want them to answer, but yeah, what happens if, so okay, if omega is finite, then can I take f to be the power set? There's no problem there. There's no ambiguity at all. So what happens, suppose that omega is infinite, then what happens? In particular, what happens when omega is uncountably infinite? That's okay. Why is that a problem? So, is this something that you thought about previously or was discussed in the probability course? Okay, how many of you have seen this ambiguity or this problem before? Okay, how many of you have not thought about this before? Well, there can only be two. Either you thought about this before or you haven't thought about it before. Right? So how many of you have not thought about this before? I see only 4 hands, which means that the rest of you have thought about this before. So the problem with, so if omega is uncountably infinite, then it turns out that it's impossible to define, so what we want to do, so given a particular omega and f, what we want to do is assign probabilities in a consistent fashion, right? So we want P what do I mean by P to be consistent? Yes. It's still okay. Yeah. Suppose we want, so the goal is to, or for a given omega, we want to be able to assign probabilities in a consistent fashion. What I mean by consistent is, now given any particular event in f, suppose I can write this in 2 different ways, as a countable union in 2 different ways. So it's equal to union I equal to 1 to infinity ai, but it's also equal to union I equal to 1 to infinity ai prime. All right? That's reasonable to expect, right? For example, if you take the interval from 0 to 1, I can decompose it as a union of interval from 0 to half and half to 1, or from 0 to 1/4 and 1/4 to 1, or as 0 to half, half to 3/4, 3/4 to so on and so on, right? So irrespective of how I decompose A as a union of events, I want to make sure that the end probability that I get, the end result that I get, is still the same. Right? If I decompose things in 2 different ways, I should not get 2 different values of the probability. That is what I mean when something is inconsistent. So it shouldn't so happen that probability of, so let's take 0 to half and half to 1, and 0 to 1/4 and 1/4 to 1. So if probability of 0 to half is, let's say, half, and probability of half to 1 is also half, so the sum is equal to 1. But if probability of 0 to 1/4 is 1/4, and probability of 1/4 to 1 is also half, then now there's an inconsistency. Right? and we don't want such inconsistencies. We can't have then the probability of one is then would therefore not be well defined. All right? Any questions? Is this point clear? Okay. So suppose my A is 0 to 1, for example. I can write this as 0 to half union half to 1. But it's also equal to okay. So these two are two different decompositions of the same set, right? So if I want to find out the probability of A, then one way to do so is to take the probability of this set and add it to the probability of this set, as you would do typically, right? But it also should be equal to probability of this set plus the probability of this set, because they are disjoint, right? So if probability of this plus probability of this is different from probability of this plus probability of this, then it means that your definition of probability is inconsistent. All right? This does not typically happen in finite sets, as long as you have finite collections. But that can potentially happen when you have when you write it as a decomposition of infinitely many sets. All right? And it turns out that if omega is uncountably infinite, then there will be at least, and you take F to be the power set, or equivalently, there exists, you can find some A which is a subset of omega such that or let me say it may not be possible to assign P in a consistent fashion. I won't get into the details of this because it basically has to be covered in a course on real analysis. But here is an example which I encourage you to just look up. So it's something called the Vitali set. It's a very counterintuitive phenomena where you can decompose the same set. So you can take the interval from 0 to 1 and you can decompose this weird set in two different ways, and the lengths of the same set computed in two different ways turn out to be different values. All right. So to avoid such inconsistencies, you look at a restriction. You, instead of taking the entire power set, you take a smaller subset over which you can define probabilities consistently. All right. And that is why we look at smaller sigma algebras or smaller event spaces than the power set. All right. So in general, we'll be looking at omega equal to R or some subinterval of R, and F to be the sigma algebra generated by intervals. So you take F to be the collection of all possible intervals of R and take all possible countable unions, intersections, and complements. All right. That's going to give you some sigma algebra. There's a proof that is required to show that you can construct a sigma algebra in this particular fashion, but it's intuitive. So this is what is called the Borel sigma algebra. All right. And why is this useful? The reason why this is useful is because now if you tell me the probability of any interval, right, then I can find the probability of any other event. Because every other set in this sigma algebra can be expressed as a countable union or intersection, basically a countable union of some sets of intervals or complements of intervals. All right. So for most of our purposes, it is enough to focus on this Borel sigma algebra. And inherently, the Borel sigma algebra is what you use when you define the CDF. Right? Because what is the CDF of a particular random variable? So it's basically the probability of that the random variable is less than or equal to some particular A, which is effectively the probability of the set minus infinity to A. Right? So it turns out that if you know the CDF, then you can compute the probability of any other event, because you can express this as either as a countable union of intervals or complements, intersections, and so on. Using just countably many basic operations, you should be able to compute the probability of any other set. All right? And that's precisely the reason why you look at a restriction. Because potentially there could be other sets which cannot be expressed as a countable union, intersection, complements of intervals. Right? So in that case, how do you find the probability of such a set? You can't. Right? Because if all you know is just the CDF, then probabilities of such events cannot be computed. All right? So that's another fundamental bottleneck, which is why you restrict yourself to something like the Borel sigma algebra. All right? Any questions? Okay. So in your probability course, have you seen Markov's inequality, Chebyshev inequality, and Chernoff bounds? Is there someone who has not seen this before? Okay, good. Let's quickly recall what Markov's inequality is. So let's say that F, can someone say what? It's a non-negative random variable. And let's say mu is the expected value of x. expectation of x, which is mu, by alpha. Right? So hopefully you've seen this before. So this is less than or equal to sigma square by alpha square. Right? Any guess? So this is less than or equal to phi of t divided by t times alpha. All right. How do you derive this? You use Chebyshev. So the approach is you have x greater than or equal to mu plus alpha. You take, this is equal to probability of x minus mu greater than or equal to alpha, which is equal to probability that e to the power x minus mu is greater than or equal to times t is greater than or equal to e to the t times alpha for t greater than 0. And this you upper bound using Markov's inequality. Right? Yes. Yeah. It depends on whether you want to take the centered moments or not. All right. So I think this is a good point for us to stop. I've also uploaded some lecture notes in the Google Drive folder. The link is in the course page. Please go through that. It contains a little more than what we've covered and gives some sort of a preview of what will be there in the next class.